But for now, I'm about to welcome to the stage Dr. Meisner. Aaron is an astronomer at NSF's National Optical Infrared Astronomy Lab. He was also a NASA Hubble Fellow at this lab, or is the NASA Hubble Fellow at this lab. He graduated from Harvard University with his PhD, and before that, I believe he went to Stanford, if his website is correct, which it appears it is. So, Aaron is very smart. We should all listen to him and learn a lot. Please.
Yeah, thanks a lot, Megan, for the introduction. I'm really impressed that on multiple occasions you remembered the entire acronym for NSF's NOIRLab, which was extremely long. So yeah, I'm an astronomer at this institution called NSF's NOIRLab. It's in Tucson, Arizona, where you can think of it essentially as like the U.S. National Observatory for ground-based optical and infrared astronomy. So we manage a lot of the telescopes for the U.S. astronomy community. Some examples being like the big 8.1 meter Gemini telescopes that are in Hawaii and Chile. So today I'll be telling you about my work on crowdsourcing the hunt for nearby worlds. And just to jump right in, one of the most timeless quests in the history of all of astronomy is to theorize and then go out and look for potential new planets in the very far reaches of our own outer solar system. And so there's a long, long history of this. You may have heard terms like Planet 9, Planet X before, Tyche, Nemesis. There's been all kinds of variants of this. But actually Neptune, which was discovered in 1846, is the only planet in the solar system that has ever been found by a correct mathematical prediction. So historically, people who have tried to make these predictions have ended up falling flat, even though in today's day and age, it generates a lot of hype, it generates a lot of social media buzz. And so Pluto, for example, which by now we call a dwarf planet, right? Not a true planet. It's not the ninth planet anymore. We only have 8. So Pluto was actually a chance discovery made in 1930 by Clyde Tombaugh, and it was based on faulty predictions that other people had been making about a large planet far out in the solar system. So even though they didn't have the right prediction, it kind of led to a nice outcome. But nevertheless, despite this bad history of making wrong predictions about potential new planets in the solar system, some people keep trying. And so one of the most notable recent examples of this is these two guys shown here who are Caltech professors, Mike Brown, who's also known on social media as a Pluto killer. He likes to really play into this whole controversy about whether Pluto should be a planet, but he also kind of likes to take credit for the fact that in 2006, the IAU demoted Pluto from a planet to a mere dwarf planet, and now just to sort of rub it in, he's got a new theory which says that not only was Pluto not the 9th planet, but now I've got a new prediction of what the real 9th planet is, which is not Pluto. It would be something more like Neptune, but about 20 times further away than Neptune. So like, I think about like 1,000 times further away from the sun than the Earth is. And then the other hypothesis, which there's different terminology out there, but I call it Planet X, and you can think of something like Jupiter or Saturn, so a much larger planet, but much further away. So think of Jupiter, but like 5,000 times further away. So this would be something like 25,000 to 50,000 times further away from the sun than the Earth is. And one thing to note about these is that both of these would be in the cold outer regions of our solar system, which influences the way that we need to go about using astronomical data to search for them if we'd like to. The other thing I'll mention briefly about the Planet X scenario is that actually it's not entirely ruled out that the object in the outer solar system, instead of being like Jupiter, it could actually be bigger. It could actually be in between the largest Jupiter-like planets and the smallest red dwarf stars. And so we call those objects brown dwarfs, and I'll talk about those a lot throughout the rest of this talk. So again, as I said, in the outer regions of the solar system, everything is really cold, and that strongly influences the way that we have to go about searching for these hypothetical objects in the outer solar system when we use real telescope data. So stars like our sun, they're very bright and they're pretty hot, you know, thousands of Kelvin is the temperature. And so that makes them readily visible in optical or in the visible light, which historically over the centuries has been what people have searched in when they make a telescope, right? It's much easier to make a telescope that gets optical light like the sunlight we see, as opposed to infrared light, which is only very recently that we've had the types of detectors you would need to be sensitive to that. And also it helps a lot to be in outer space. when you're in the infrared because of the Earth's atmosphere. So basically what this slide is showing is just that there's a continuum from regular old main sequence stars like the sun all the way down to planets like Jupiter, and in between the largest planets and the smallest red dwarf stars are these objects that we call brown dwarfs. And so at the brown dwarf to free floating planet or Jupiter like planet end here, these objects emit almost all of their light in the infrared. Ironically, brown dwarfs wouldn't look brown to the human eye, which I don't know if you can see it, but they would look more purple as shown here. So yeah, in the recent years, particularly the past decade, there's been sort of a revolution in our ability to look at the infrared universe, and it comes mainly from this NASA space telescope called WISE that's in low Earth orbit. And so every 90 minutes, WISE makes an orbit around the entire Earth. It's in the polar orbit, and it's on what's called the terminator of the Earth, so that's like the day-night line. And it looks directly out from the Earth, so by doing that, it can actually observe all the time, 24 hours a day. It doesn't really have like the nighttime for observing and the daytime for not observing, unlike observatories that are on the Earth. And so you can see that as this telescope orbits the Earth and as the Earth orbits the sun, it will gradually sweep out these large circles on the sky. And so every 6 months, WISE, yeah, as you can see here, it's scanning these stripes in the sky, which will eventually fill in the whole thing. So every 6 months during which this WISE NASA telescope is operational, you get another full sky map in this 3 to 5 micron wavelength range. You can think of that as being wavelengths like 10 times longer than the visible light that we mostly get from the sun. And so WISE is really giving us a dramatically better picture of the infrared universe that we could never do before. And this has opened up a whole new realm of possibilities as far as searching for cold and potentially nearby neighbors to the sun, like brown dwarfs or even Jupiter-like planets in the very far reaches of our solar system. Here's a plot of the sun's very nearest neighbors. So I would guess that some folks here have heard of at least some of these. For example, Barnard star is one of the closest stars. It's a red dwarf. It was discovered in 1916. And then, of course, there's the Proxima Centauri system. There's various Proximas within that system, but that's actually the closest known star or brown dwarf system to us, something like 4 light years away. And again, that was discovered, the components of that were discovered in the early 1900s or even early mid 1800s. But then the only other things that we've been able to populate this diagram with so far are very recent discoveries from the past 5 or 10 years that came specifically from this NASA WISE infrared data set. So there's this WISE 0855 discovered in 2014, and there's this WISE 1049 discovered in 2013. And these are now, I believe, the 3rd and 4th closest known systems to the sun. So they're kind of like historic discoveries because it's been a century since anyone had discovered anything this close to our own solar system. So it's really a remarkable illustration of the fact that by looking at this new infrared wavelength range, you can totally open up a new discovery space and see things that were previously invisible, even though they're super close to us by astronomical standards. So I don't know how well this is going to show, but this is an illustration of one of the techniques, the primary techniques that's used historically and to this day to search for nearby planets and nearby brown dwarfs in the sun's local cosmic neighborhood, which we call the solar neighborhood. And the basic idea is that everything in the universe is moving to some extent relative to us, but the stuff that's much closer to us appears to move faster, right? So like if you were to displace an object that's close to you by some amount, you'd see it move a lot, but if it was a football field away from you or something like that, you might not even notice. And that's the exact same principle we use here. And it's the same principle that, for example, Clyde Tombaugh used when he discovered Pluto, is that something that's moving fast across the sky, it must be nearby, and therefore it must be something interesting, like a planet, a dwarf planet, maybe a brown dwarf in the solar neighborhood. So yeah, this is exactly what I'm talking about when I say finding nearby worlds the old-fashioned way. This is an example of what Barnard star, which I just mentioned, it's a very nearby red dwarf, looks like. So you can see that from the 1985 to, I think, 2005 time period, it moves a lot relative to all the other objects in this field, which are the white dots, and they're just sitting there basically doing nothing, right? And so that's a really effective way of selecting things in huge astronomical sky maps or huge astronomical databases that are close to us. And then, yeah, this is going to be especially challenging given the lighting situation. But this is the actual discovery images that Clyde Tombaugh used to discover Pluto. And you can maybe see that there's 2 arrows here that point to the different positions over the course of like a week, and it moved quite a bit relative to all the background stars and galaxies, which are just staying fixed. Let's see if is this any easier to see? So partially this is proving my point, which is that it's a lot easier to see these things in an animated movie fashion rather than trying to stare at a bunch of pictures. So the way this was done historically in astronomy was something called a blink comparator, which this is pre-computers, right? So you have some photographic plates that you're looking at, and they're loaded in some machine. You click a button that switches between two or potentially more of them. And that's a really effective way of finding things that move or finding things that change. It's like those, online advertisements or whatever. It's like find 6 differences in this In-N-Out restaurant between these 2 pictures, and they like remove the sign, but you couldn't see it if you were just looking side by side. And then when you blink, it's super obvious what changed. So by nowadays, we don't necessarily need to use that type of technology, which is kind of antiquated. I don't think I've ever used a blink comparator. I actually had to look up today how it works, so I was kind of confused. But what we do now is all computerized. It's all online, right? And we have these massive databases of image catalogs from modern telescopes. And so I like to think of this as going from amateur astronomy that's based in backyard observatories versus going to amateur astronomy that's based on the internet and online data now. So one example, going back to the 90s, I used to like putting this in my talks when I was in Arizona because Thomas Bach was an amateur astronomer who discovered the comet. Hale-Bopp co-discovered it in 1995. There's probably not many good amateur astronomer examples from Seattle, just given the weather here, so I didn't even try. I'm originally from Bellevue, by the way, so I don't know if that's a good thing or a bad thing in this context. But so yeah, nowadays you can still do that, but there's a high barrier to entry, right? Because it's not every person who can set up a backyard telescope and have all this machinery, all this equipment, and fine tune it and pay all those expenses and devote all this time. So we think that a sort of, in some ways, better and more inclusive way of doing this is online. And so there's different terms for this: citizen science, community science, crowdsourced science, participatory science. This one says people-powered research. But the idea is just to put lots of your data online and then let anyone look at it. They don't need to have any particular background, any degrees, any formal education in astronomy. And one popular platform for this is called Universe, which is what we use to launch our citizen science projects. It has all kinds of citizen science projects on there on this Universe, like, ranging from like marine biology and genetics and history to astronomy. So it's quite a range if you're interested to look it up. So yeah, one thing we've seen in this new like data-driven, online-driven era of astronomy is that there's a real huge value in mining these massive data sets through a combination of different techniques. Of course, we do things like use supercomputers and machine learning, but then the citizen science human element also comes in and plays a very unique role, in my opinion. One of those unique roles is to find really weird outlier objects that, for example, you might not have trained your algorithms to find in the first place. And so this one, which may be hard to see, is Hanny's borer. I'm sure I'm pronouncing that wrong. But it was discovered by Hanny van Arkel, who is a science teacher, I believe, in the Netherlands, and it's sort of like a new class of active galaxy that had never been seen before. So this is an example of discovering weird and new things that you maybe couldn't have done without the human element involved. Another one that you may have heard of is called Tabby Star. It was also referred to in the press as the WTF star, where's the flux? But it has this really weird, totally unprecedented light curve, where light curve means how bright it is as a function of time. And several astronomers were quick to point out that this looks exactly like what you might guess you would see if you had some sort of alien megastructure around a star. So it was big in the whole SETI realm, search for extraterrestrial intelligence, because of that. It has turned out to be more favored to be some sort of natural phenomenon, more like dust encircling the star, but nevertheless, it's a great example of like a totally new field of research that was opened up by crowdsourcing the inspection of these large astronomy data sets. So yeah, that brings me to the astronomy project the Astronomy Citizen Science project that I co-founded back in 2017, which is called Backyard Worlds. The full name is Backyard Worlds: Planet 9. So the idea is that we take all this huge volume of NASA data from the WISE telescope that I mentioned. Again, it's on the order of tens of trillions of raw pixels of data, billions of stars and galaxies in it in total. So there's lots to mine, lots to look at. And we basically just take that data online in the form of maps, We give it to people to sign up and look at, and they look for things that move, just like Clyde Tombaugh looked for Pluto. Well, he was really looking for a planet, but he found Pluto by looking for things that move. So this is like a promotional video that we have for our Backyard Worlds project. You can see that it's showing the context here. So you have the planets, which you probably know pretty well. Pluto was in there, I would believe. But then astronomers think there's now this new ninth planet, Planet 9, as I mentioned, which is way, way further out in the outer solar system. It'll be shown here in a second. Yeah, so Planet 9 is way, way out in the solar system. As it says, no one knows its exact position or mass or size, which is why we need to do this type of crowdsourced approach using big data, because we want to scour the entire sky. We don't really have a firm prediction of where exactly we need to look like they did in the case of Neptune. And then now we're going even further out. We want to explore the territory beyond the solar system. As I was mentioning, it's going to get into the part about brown dwarfs that may be very cold and nearby, lurking in our own solar neighborhood. Relatively speaking, these are a recent discovery. So, I mean, stars have been known for, I assume, thousands of years at least. But brown dwarfs have only been known since 1995 in the sense of the first one was detected there. As it says, NASA's wide spacecraft has led to the discovery of two special brown dwarfs, which are the exact same ones I talked about before, WISE 0855 and WISE 1049, also known as Lumen 16 AB. So these are very, very nearby the sun. This is showing kind of like the three-dimensional view of these objects in the solar neighborhood. And this is making the connection now to the NASA data that we're showing in the Backyard Worlds project, where we're blinking these time series images of a fixed point on the sky and looking for things that move. So right, you can now see that there's these two new brown dwarfs that are extremely nearby, and they join some of the nearest known stars like Barnard stars. So it's kind of like a three-dimensional view of the two-dimensional picture I showed earlier. So yeah, I just wanted to go into a little bit about how this project has gone. It's been really fun. I have to admit, I was skeptical at first because I was like, well, I have access to supercomputers. I can write code. Like, surely I can just discover all the stuff on my own. But it hasn't turned out that way. And all the stuff we've discovered, I wouldn't have found it on my own. I didn't find it on my own before the volunteers did. It's just been really productive, both scientifically and from the sort of public engagement standpoint. We have about 80,000 registered users. We think that we have about 200,000 unique participants who have contributed to the project at some level, because you don't actually need to register to participate. Quite a diversity of backgrounds in terms of the people who contribute. They range from like high school students, college students, retired engineers, stay-at-home parents, you name it. And there's also a lot of geographic diversity. So we have people from all over the world. I believe at one time we checked our Google Analytics and found something like 167 countries represented, all 50 United States, plus Puerto Rico and DC. One thing that we've tried really hard to do is to sort of build a community beyond just dumping data online and telling people to look at it, right? So we've taken a lot of effort to identify what we call our super users or our advanced users who are really engaged, make really big disproportionate contributions relative to someone who just comes and clicks a few things one time and doesn't return. So what we've done is that we have these weekly science team calls of Backyard Worlds, where they're on something like Zoom, or I think in this case it's Google Hangouts. And every week we invite all 300 of our super users, who are generally not professional scientists, not professional astronomers, to join our calls. And this was a really fun moment where we sort of realized that David here was calling in from his high school library at lunch period, which I thought was awesome, because I don't know what I was doing during lunchtime in high school, but it definitely wasn't being on a telethon with professional NASA astrophysicists. So yeah, just to give a flavor of what we're looking at when we make these discoveries, we've had a lot of success discovering new brown dwarfs near the sun. We haven't discovered a Planet 9 or a Planet X. I think we can take that as a given, otherwise it probably would have been some sort of news story. But this is what we're looking at, and you can see basically that this is the WISE data. Most objects look this normal-ish plain color of black. Those are normal stars and galaxies. But in the middle in each of these, you can see that there's something moving around, so it's not static, and it also has, maybe you can see this, a sort of reddish-orange color to it, and that indicates that it's very cold, and that gives us a clue that it's a brown dwarf rather than a normal main sequence star. The other really fun thing we've been discovering a lot of in this project is what we call companions to higher mass stars. So you can kind of think of this as like a planet scenario. So it's like an oversized version of Jupiter, but orbiting a nearby star at, in this case, hundreds or thousands of AU. Unfortunately, I can't read the labels, but these are all kind of in the 400 to 1500 AU range in terms of the separation from the host star. So what that means is that these objects are kind of like 1,000 times further out from their host star than the Earth is from the sun. And they're kind of Jupiter-like, but even bigger. And so I like to think about this as, we're kind of seeing the Planet X scenario play out, not in our own solar system, but in nearby systems. So that's kind of the next best thing. And I think it's really cool to be able to see these objects. And there's kind of like an odd satisfaction in just seeing the two objects in the field of view, like moving together. So hopefully this shows up well, but just to say, we discovered something like 4,000 new brown dwarfs have been discovered by our volunteers since we launched in 2017, which comes out to about 1.7 brown dwarf discoveries per day on average. This is a 3D rendering of all the brown dwarfs we discovered. And again, since because of the fact that we detect them based on their motions, that's how we discover them. We know how they're moving through space. And so what we can do here is speed up their evolution over time by a huge factor. So when you see these things move, you're seeing millions of years play out in seconds. But what we can do is, given that we know their motions from discovering them, we can predict how they will disperse all throughout the Milky Way galaxy over time, which I think is super cool to look at and visualize. Here's another visual of our discovery. So this time we're zooming in on the Milky Way from outside of it. So the sun isn't right in the center of the Milky Way, right? It's in some outer spiral arm or some general outer area. And now we're zooming into the solar neighborhood, coming in from above the plane of the Milky Way galaxy. And we're seeing the same 3D rendering of all or at least some subset of our backyard world's brown dwarf discoveries rendered in 3D. Unfortunately, this one doesn't play the motions, I believe, but nevertheless, you're seeing the 3D positions of like millions of stars here as well that come from various modern astronomical catalogs. And then here you reach the solar neighborhood where you see the backyard world's citizen scientist discoveries in 3D. One other really fun part of Backyard World is that it's a real kick for a lot of our volunteers when they get the opportunity to have one of their discoveries followed up with one of the biggest telescopes in the world or in space. And so we've had a lot of success at getting our brown dwarf discovered by members of the general public, observed by some of the biggest and best telescopes in space and on the ground, examples being the Gemini 8-meter telescopes, both in Hawaii and Chile, the Blanco 4-meter telescope in Chile, the NASA IRTF telescope in Hawaii. We've even had citizen science discoveries from Backyard Worlds that have been observed by Hubble Space Telescope and Spitzer Space Telescope, which are, of course, two of NASA's great observatories. And then most recently, we have had some success at getting our citizen scientists discovered brown dwarfs observed with JWST, which is awesome because JWST is kind of all the rage nowadays in the astronomy community and also in the popular astronomy press. So yeah, I just wanted to somewhat conclude. I think I have a couple more slides, but I did want to mention one of our best discoveries that is now soon slated to be observed by JWST. And it fits in with the theme from before about how Pluto was discovered accidentally when looking for what they thought was something else that was going to be there. And so sometimes the best discoveries happen by accident, and this is one case. I'm guessing, given the lighting, no one can see the object, but we have a very talented citizen scientist in the tech industry who likes running his own machine learning algorithms on the full sky maps, all the pixels, all of that. And he thought he had a really nice brown dwarf candidate right in the center of this picture here. And it turned out he was wrong, but there is, I'm doubting you can see it, right along the bottom corner there is a moving object, which is extremely faint and moving extremely fast by astronomical standards. And we nicknamed this, well, actually, the discoverer nicknamed it the accident. And that is a technical term that's been used in the literature by now. And so the text here says, this is from an article in Quantum Magazine. Dan Castleton was up late on November 3rd, 2018, playing the video game Counter-Strike when he made astronomy history. Every time he died, he would jump on his laptop to check in on an automated search he was running of NASA Space Telescope images. So it just goes to show you that by having a lot of eyes on the data, you can discover cool stuff. And so for the upcoming JWST cycle that runs from this summer to next summer, we did get allocated about 8 hours of James Webb time to specifically look at this object. So I think it's a great story in that it's scientifically important, but it's also cool to think that something that a member of the general public discovered is now being observed by JWST. Just to try to preempt questions that I may get, what about artificial intelligence, right? Like, why can't we just do this all with machine learning, with ChatGPT, Google Bard, etc.? And I think the narrative that I would like to pitch is we can't ignore AI and machine learning, right? Those are coming down the pipe. They're pretty impressive already. But I think that AI and citizen science can be complementary. So for instance, supervised machine learning often needs large, what we call training data sets, large samples for that. And that can be provided. For example, one way of doing it is through crowdsourcing of the human inspection components, where you can do a lot more in a much shorter time by distributing small amounts of work to a lot of people who are enthusiastic rather than trying to do it all with a small group of professionals. So in my last slide, I wanted to mention that yesterday we just launched a new spin-off citizen science project at Backyard Worlds called Backyard Worlds Cool Neighbors. And the idea is to kind of merge in the machine learning part with the citizen science part. So we're using machine learning to optimize what gets showed to the volunteers. And you can join, anyone can join. I would encourage it. You just have to visit coolneighbors.org. That's our logo. So I'll leave it at that. Thank you. I can try to take a few questions. I can't take this mic to someone, right?
Yeah, you just have to talk loud, like me.
Did you say what the accident is?
We're not sure. It's totally, what we do know is it's totally unlike any other known star or white dwarf or brown dwarf. We think it's a very ancient brown dwarf. So in astronomy terms, we call this low metallicity. So it has a relatively low amount of heavy elements in its atmosphere. So it could also potentially be that it's just low metallicity and it's in what we call the Milky Way's halo, which is kind of the most ancient part as compared to the disk right nearby us, which is younger. The other possibility that was more speculative, but we did kind of float it when we were asking for JWST time, is that it could be weird because it's like essentially visiting from another galaxy. So the Milky Way halo is not just a bunch of random stars, right? It was built up through a combination of different accretion events of different progenitor galaxies. And so one of them, for reasons I don't really understand, is called the Gaia sausage progenitor galaxy. I'm not really that big a fan of the name, but interestingly, we can make a measurement with JWST that would tell us whether it comes from this progenitor galaxy or whether it's a more normal version of a brown dwarf in the Milky Way's halo. But it would be cool to be able to say that we have found a visitor to the solar neighborhood from another galaxy. We'll have to see what the data comes out as.
What's the threshold for an observation like this to be to get JWST time? Like, what do you have to do for?
Yeah, the question was, what's the threshold, or what do you have to prove to get JWST time? And it's an extremely high threshold because it's super oversubscribed at this point, just because of the fact that it's really got an unprecedented and unrivaled ability to see the universe, especially at infrared wavelengths. So, for example, in the most recent cycle, where we did get the time to look at the accident object, I believe it was oversubscribed by a factor of like 7 in terms of people requested 35,000 telescope hours worth of observations, but there were only 5,000 available given how much time there is in a year and the other constraints on the spacecraft. So the answer is like a factor of 7, which is, I think it was historically high, even compared to like Hubble, for example.
The white objects in the early or the planets that we get out on the form. What are the clues that are they about? And if so, how specific are they telling you where?
Yeah, so the question is, why do you think that something like Planet 9 exists? And so I'll just take Planet 9 as an example. And yeah, one of the suggestions you made was gravitational anomalies. And so that was indeed the first evidence for this proposed by Mike Brown and Konstantin Weigand at Caltech. That has been disputed a lot, though. I mean, people have come at it from every angle. What they were looking at is what are called these extreme transient Neptunian objects, ETNOs, and they have this weird property that the closest they get to the sun is pretty far out relative to like even Neptune, and so they're outside of the gravitational influence of all the usual suspects in the inner solar system, the planets that we know about, and so that led them to hypothesize, well, one mechanism that you could get for forming and maintaining this population of objects is a massive planet in the outer solar system. And then there's been a lot of back and forth over the years about whether that is a robust statement or not. People have kind of attacked it from different angles, like, oh, is there a bias in terms of what objects you select? Are we really detecting the true population? Things like that. So that's basically the answer to that gravitational effects. Yeah.
So this hasn't launched yet, right? Well, neighbors, or it did just.
Like yesterday, I think.
Okay, so I haven't gotten a chance to look at it yet, but I was wondering, what are the labeling tasks and how was that?
Sure. Yeah. So the question is, how does this Cool Neighbors project work? And I can also answer sort of like how it's different from the original predecessor, Backyard Worlds, Planet 9. So as I said, one of the big changes here is that we use machine learning to pre-select what gets shown to our volunteers. So in the original Backyard Worlds Planet 9, we just showed totally random sky patches to people covering the whole sky. And by now, we've had people look at 8.5 million of these images. And so it equates to something like looking at the whole sky 6.5 times over. So we've done well at that, but wouldn't it just be better if we could tell people exactly what to look at? So that's what we've done. And we've also simplified the classification. We call this classification in the universe parlance. We've simplified that a fair amount. So in the original Backyard Worlds Planet 9, it was a very open-ended task. It's like, click on anything in this image that you think moves, and you could have like huge numbers of clicks. I think someone once clicked like 1,000 objects in one little patch of the sky, and we thought maybe they had like come home from the bar and like fallen asleep on the keyboard or something. But it's a kind of like an open-ended data analysis task on our side. And then in this case, we were just like, let's make it much more concrete and specific. And so the idea was to have it be a very simple, like Boolean yes/no task. And you just say, is there an object near the center of the frame that's moving or not? It's yes, no. And so we think that'll make the data analysis a lot easier, although we're only one day in, so it's a little hard to say. But we do things like beta tests where we do a test run of a much smaller data set and get a lot of input for each patch of the sky so that we can kind of run tests about like, are we going to be able to do statistically robust things with the data given what we're collecting.
You're saying there's like different class objects, like 1,000 to 50,000 distance in the earth. How does that compare like the distance of the blade? How much further out the blades are than the 1,000 times like district blade?
I don't actually know the distance of Voyager right now, but it's kind of like I think, isn't it kind of like somewhat larger, but on the same order as Pluto, essentially, you know, many tens of astronomical units, many tens of times further out.
You just asked the heliopause.
Okay.
It's 159 astronomical units.
Okay, so I was kind of in the right one. So the question was, how does it compare to Voyager? So then, yeah, most of these hypotheses don't have something at 150 AU, 150 times further than the Earth is from the sun. The Planet 9 is the closer hypothesis, and that posits something at kind of like 600 to 1500 AU. So that's substantially further out than Voyager. Then the Planet X scenario is even further out than that. That's many thousands of times further out from the sun than the Earth is. So it's not. Basically, the problem is you can't have something too close and still be an actual planet, right? Like if it was really close and big enough to be a planet, then it would be super bright and it would have been discovered by now. So that's kind of like the constraint that you're playing around with here. Like you couldn't hypothesize a Neptune-sized planet at 100 AU and not have been discovered already. So you kind of have to paint around the existing constraints there. There have been interesting attempts to constrain whether Planet 9 might exist using spacecraft in the inner solar system, like I believe it was using Cassini metrology of its like exact distance from various objects. I can't actually remember the outcome of that, but people have tried that, and I don't know whether it would make sense or not to try with Voyager, or what kind of telemetry data they get from Voyager exactly.
Voyager 168.
Okay, thanks. Yeah.
Yeah, sorry. Two-part question. First of all, are your databases being updated currently, or are you going off like a static database? And the second part, if it is currently being updated, how are you adjusting for things like the satellite constellations like Starlink, and how the evolution of those are kind of making a bit of a mess for ground-based telescopes?
Yeah, so those are good questions, relatively technical too. So this WISE mission is the source of all of our data, but they only release their data on yearly cadence. So I basically get a big dump of like 35 terabytes worth of data, about 5 million images once every spring. And then I do some processing on a Department of Energy supercomputer that I have access to. And that happens once a year only. It would, in my opinion, it would be nice if the mission were to release its data on a rolling basis, but I assume there are funding constraints about why they can't make that a reality. As far as Starlink and other satellite constellations, I haven't particularly looked for them in this data set. I can tell you, so first of all, this is the space-based data set, which perhaps helps a little bit, although some of the Starlink satellites are above low Earth orbit. I can tell you that I've worked on other telescopes that are on the ground, specifically the Mail telescope at Kitt Peak, which is kind of near Tucson. And we have this little, we call it a pointing camera that is on the top ring of the telescope. And it's a commercial camera that just takes images of a wide field of the sky. And you see tons and tons of Starlink satellites in there. So, I mean, it's definitely real, but I don't think it's catastrophically impacted really anything at this point, and it's not helpful for ground-based astronomy. Now, maybe you can argue that SpaceX is helpful for space-based astronomy, which I think there probably is a good argument for that. But the other thing is that there's a lot of redundancy in this WISE satellite data. So every time it makes a mapping of the sky at each sky location, it actually gets something like 12 or more images. And so there's a lot of room to do something like outlier rejection that just deletes anything like satellites, or even for our purposes, we consider asteroids to be kind of like outliers that get rejected in that image processing.
Let's give our speaker a round of applause. Okay. Yeah. Okay, so I'm back. It's louder than ever. Before we get on with the trivia winners, I'm just curious who's gonna check out Backyard Worlds and Cool Neighbors. All right. Okay, cool. So back to trivia. So we have one winner to rule them all. We do. One person that won by a landslide, and then they also, this person that won by a landslide also tied in both of the round winners, but they can only win one. Okay, so then we also have a tie for, was it not that? Okay, we have a tie for the sci-fi questions, and we have a winner for the women in astronomy. And then I have 5 honorable mentions who sadly did not win, but I liked your team name so much that I'm going to say them into the microphone. But before I do any of that, here's probably the announcement.
I'm just coming to listen here. No one listens.
Usually,
I know, I usually say something in between people. I'm Frank Castro, my wife Sean is in there. We're the owners here. Thank you all for coming out tonight. Yes. We'd love to have you on every month. I'm hoping for some of you, the cycle dogs worked out tonight. This is the first time we've had a big group that's working out. So we'll have that as an ongoing thing, working with them. So thank you all for coming out. See you next week or next month.
Okay, now before I announce the people, let me go through the answers. So, sci-fi questions. A true story was the first science fiction novel, apparently, according to this PowerPoint. John Carter was based on A Princess of Mars. Rod Sterling narrated and produced The Twilight Zone. Riverside, Iowa is where James T. Kirk was born. How was the biggest computer in the Space Odyssey? The Jedi. Was not Shape of Water. Marie Curie won the Nobel Prize in 1903 for research radiation. Lisa Meitner led the group that discovered nuclear fission of uranium. Marie Goeppert-Meyer was the theoretical physicist that first proposed the nuclear shell model. Christina Koch set the record for most days in space of any woman in a single mission. Mae Jemison was the first Black woman in space. Jocelyn Bell Burnell is credited with observing pulsars, and she should have gotten the Nobel Prize. Right, and she's really cool, by the way. Like as a person. Okay. Margaret Hamilton was credited with creating the term software engineering while developing the software for the Apollo spacecraft. Peggy Whitson logged the most days in space for any American as of 2020. They're really everything. You should mention also, Aaron, are you affiliated with Rubin Observatory as well? Are you working? Everyone at that table works with their There's a lot of folks at UW. Okay. 28% is the percentage that women make up in the science workforce. We gotta get those numbers up. Okay. Published. I'm gonna save my favorite one for last. Okay. Ultra Serious. Like the Star series. Schrodinger's Dogs. George's Black Hole. And then my personal favorite team name, because I learned something. It's not Pi Day, it's Tau Day. But let me explain the joke for those of you. So, Day is March 14th, 3/14, and Tau means 2 pi, and today is 6/28. So everyone this team name, I did not either. You guys can okay, so now I'm going to move on to the winners of trivia who also have good team names. First off, the one winner to rule them all, who gets to pick their prize first, is Beetlejuicy. And now the round winners who fight to the death for who gets to pick their prize first. I'm just kidding. Thanks for laughing, those of you that did. Okay, so starting with the sci-fi questions, we have a tie for the sci-fi question winners. So in no particular order, one winner is Geoff News. Is that? Geoff News, sorry. And the other winner of the sci-fi questions is 8 light minutes, which is the distance to the sun. the winner of the Women in Physics and Astro round is CST. Check it out. Please come collect a prize, and posters are a good thing. We also have stickers, so don't worry. And before I let you go entirely, so that you can drink beer and go home or whatever you're gonna do, I just want to announce that the next Astro on Tap will be on July 26th. And I was on top of it, and I already have speakers lined up for both July and August. Those announcements. And I have one more really exciting announcement to make that I wanted to share with you guys. So you guys are fantastic. Did you know this? You guys are fantastic. And you're all really good. It's just such a great turnout for Astro Tap. You guys participate to such a high level. So I've been trying really hard to make Astro on Tap better with the help of my Astro on Tap co-workers, Sam Garza and Jess Berkey. And we have convinced the Department of Astronomy to help us bring speakers from other institutions starting in the fall. And so that will begin in October. And I wanted to announce that. July 26th. Yes.
Field juice.
Okay. Posters, sticker. You got you can look at it. There's another great one.
Yeah. I don't know. Japanese. Yeah, somehow I assumed she was involved with completing it. Maybe she's not. Okay.
Did you have a